So dynamics is the study of why objects move, whereas kinetics is the study of how. So when we talk about forces, this is either a push or a pull. This is measured in newtons, which we go capital N. So fill that blank in there. Measured in newtons with a capital N. It is a vector quantity because force has direction, right? When we were rolling our Play-Doh across the table, we were giving it a certain direction. Gravity has a direction down, okay? So we need to include the direction of force. Okay, next, a net force, as we just said, is defined as the sum or total of all forces acting on an object at one time. Now, when we have an unbalanced net force acting on an object, it will cause the object to accelerate or decelerate. So it's going to move. Therefore, an unbalanced force will cause an object to experience a change in velocity. So this unbalanced net force, this was like when we played tug of war and the grade 11s. Creamed you. Okay, so the formula that we use for this is known as Newton's second law. So this is F with your arrow over top of it because it's a vector quantity. F net is equal to M times A. On your data sheet, and oh, I should put the arrow over top of my A as well because we know acceleration is a vector quantity. On your data sheet, I'm pretty sure it's represented as A equals F net over M. Let's get out our data sheets.
What's his first law?
We'll do that another day. It's all about inertia is the first law.
So we went second law and then first law?
Yeah, it's just, it doesn't matter that you find, like the second law, understanding this is fundamental to the whole unit. So we're doing it first. Yeah. It won't confuse you that we'll do them out of order. Oh, you handed it in with your test, so I put it back into the handy box. So, yeah. I'm pretty sure I do.
It's not here.
I can't remember, but here, you can take mine. I knew I found it.
You're right.
So, now where we're looking is under the black margin that says dynamics. Dynamics. Because this is the unit we're in, so all of these are nicely organized according to your unit. So we've done all our kinematics, now we're into dynamics. So you can see there that A is equal to F net over M. So this is where F net is our force net acting on an object. M is the mass in kilograms, and A is acceleration. Now here, this is different because like before we'd have meters and seconds and meters per second. But now we have newtons, kilograms, and meters per second squared. Well, those don't kind of mix together unless I tell you what a newton is. You want to know? Oh, I know you do. A newton, it's units because we kind of group it and say, well, it's a newton to make things easier. It's like saying I've got a bushel of apples or something, or a dozen of apples. Anyways, okay. A newton is a kilogram times meters per second squared. So say you have, right, because if I was going, say I had a mass of 12 grams and its acceleration was 2.53 meters per second squared. To find F, I go 12 kilograms times 2.53 meters per second squared. If I take these units and multiply them together, whatever this is, so 12, okay, so 30.36. My units, I could write it as kilogram times meter per second squared. That's correct. But scientists have said, that's silly. Let's make one unit that describes all of this. So then you can write it as 30.36 newtons. See that? I do more examples, but that's why we can just take this information and summarize it just into newtons. That's what a newton means. Huh?
Yeah.
Good, okay. Really, does that actually make sense? Do you guys follow me? Sometimes I don't know. You know, sometimes I feel like I'm just saying stuff. Okay. So this equation, all this, was Newton's second law of motion. So that's a blank there, I think. Nope, never mind, sorry. Yes, it is.
Yeah, it is.
Yep.
The one before that.
See, there's a mistake.
This, oh, where did it go? That thing that's right above there, just cross that out. That's fine. Oh, no, it should be a balanced net force. Haha. A balanced net force occurs when an object blah blah blah. Okay, sorry for the confusion. Then, as said, the above equation is known as Newton's second law. So the change in velocity of an object is proportional to the net force and inversely proportional to the object's mass. Well, what the heck does proportional and improportional and inversely proportional mean? Well, let's talk about that. Okay? So proportional, so what we think about this means as the manipulated variable changes, the responding changes the same way. That's all it means. Okay? It's like eating food. The more food you eat, the more full you get. That's proportional.
What sign is in between A and F?
Oh, I tell you. A, so this is saying A, it's like that. A, this symbol means proportional. So A is proportional to F net. If force increases, acceleration will increase if the mass stays constant. So if I'm dealing with the same object and the force of that object increases, the acceleration will increase. So I have my ball. This is the same mass. This, whatever mass it is, it's going to stay the same. Oops. It's okay. So I push with a force of a little bit. Its acceleration is not that much. This needs to be more round. And then I push with a stronger force. It's going to have a bigger acceleration, right? Bigger force, bigger acceleration. So sometimes these don't need to be memorized. Because if you think about it logically, you know the answer. When I push something with more force, it moves faster. Okay? Now, inversely, oh, and we should do this. Okay, so if say we have a little graph. Let's put acceleration on the side. is in meters per second squared. And our F net is our horizontal in newtons. So if F net increases, acceleration will also increase. So we see a proportional representation on a graph. So now, inversely proportional. As the manipulated variable is changed, the responding variable changes in the opposite way. So, A is proportional to 1 divided by the mass. So we can write this as A is proportional to 1 over mass. So we still use the proportional sign, but now we put 1 over m. Because look at our formula. A is equal to F net over m. Look at where A is in relation to m. Okay, that shows their relation. They're inversely proportional. So when I put, let's say A goes on my vertical side again, my y-axis, and mass is in kilograms.
Is there 3 of them?
No. Oh, sorry, the graph. Just draw it in on the bottom of your thing, because I didn't give you the lines. Thank you. So, say again with my ball example. Let's say I increase the mass of my ball, okay? And I push with the same, and I get the same force. So force stays the same, okay? Force stays the same. It's going to roll slower because it's bigger, right? So I get a bigger and bigger ball, and I push with the same force, but it doesn't go as far. Right? It doesn't have as much acceleration. So that's why if we see high mass, or low mass, so this is like a low mass, I would have a high acceleration. As I increase in mass, my acceleration will get lower and lower until it will level out, because it will have a certain level of acceleration, and then it won't go anymore.
So acceleration will never be a stop with the mass.
Well, but technically it could be, right? Because you could physically not move any. If something gets so big, if you use the same force, you could potentially not move it at all. So it would theoretically go to 0. So think about it like making a snowball, right? The bigger the snowball gets, you have to push with more force to keep it going, to keep rolling, right? Huh? Yeah. See, you guys were studying physics when you were like 5.